Hello and welcome to PCAM Lab. Today we're going to do some hydrogen spectroscopy, right? We're going to be looking at the visible spectrum, visible out to UV. We've already shown you how to take that data of the visible to UV spectrum of the hydrogen atom. And now what we want to do is to turn that data, right, that we got from the hydrogen atom into a value for the Rydberg constant. So that's what we're going to do here, right? So we know what the data should look like, right? We're dropping down to a lower level from excited states. We're trying to determine what levels are in here. And as we converge on the ionization limit up here, the states get closer and closer together. So we should see lines that get closer and closer together according to following that wave number pattern of the Balmer-Rydberg-Ritz formula. Okay, so we took some data, some survey scans, and then we found out where the lines were. We went over those lines at high resolution. Then we crank up the voltage and we do some longer scans out in the UV. All right, so now what we want to do is take that data and turn it into some values, right? So in order to do that, we're going to crank up Igor Pro and let's load some data and then do a little bit of analysis on that. I want to remind you of how to do that. So where's the data? I'll have that up on D2L shortly. We're going to load some general text, right? So we're going to load some general text. This data was taken by Paige Kogelman, some excellent data that she took back in the day. And first of all, right? Okay, so the data as it comes out of the data acquisition program, it always gives the two columns the same numbers. We don't want to write over the data. So now there's a wavelength, the lambda is wavelength, right? And we have a bunch of these. So let's call that 656. And then there is the intensity in volts, the signal level, right? And we're going to rename those so that we can load them in, and then we want to plot them, right? We want to make a spectrum. So let's make a new graph under Windows there. You're going to have intensity versus wavelength, the lambda value, boom. Here's our first peak. That's that one out there in the red. All right, that's what our peak looks like. Let's make this look like a spectrum, right? Okay, so the bottom axis, the label for that is going to be wavelength, and that's in nanometers. And the left axis, that's the signal, and that's measured in volts, right? Now the axis, oh, I always like to put that mirror axis on those. It gives it that little box, makes it look cool, right? All right, what else do we have to worry about? Nothing for now. We got one peak. There we go. Data goes over that value. Sure enough, looks pretty good. And we're getting that to look like a spectrum. We load in the second one now. Again, we have to rename. There's the wavelength, the lambda value. Now it starts off at 486 is obviously the nanometers where it starts, right? And I'm just going to use a systematic name here so that we know what we're dealing with. Boom, and we can append that to this graph, right? We just go up here, append 486 versus 486, and oh, okay, there's the first peak, and much smaller peak further away out here. They're very narrow peaks, right, compared to the huge amount of expanse in between them. So we'll load the next one, right? And got to change the name again. Wavelength value, this one starts at 434, so let's just call it I434, then boom. And again, we can append that to the graph, 434 versus 434. And now, there we go. We've got something that's starting to look like a spectrum. We're seeing a trend here in the intensities as they're dropping off toward, this is the blue end out here. Now, eventually, we're going to cover a whole range from the UV out to the edge of the red of the visible. We're going to want to fill it. You can see that they're getting close. They're losing intensity as we're going out to the blue. They're also getting closer together. All right, good. We've got something that looks like a spectrum there. What does the rest of it look like? Well, let's go back here. I'm not going to save that right now. Normally, save your data, of course. Get all the data that we collected at 700 nanometers. What we see is the intensity is falling off as we go to the blue, and they're getting closer and closer together. And then we really just start to run out of signal, right? Now, if I have something like this that looks like a good good graph and that I want to use again, which I did exactly in making up this example, and I want to save this, I can click on that red dot and I can give it a name and say save the first time. Later on, it will be replace, right? Now, what we did was first, we took some data at 700 volts, right? So we started running out of signal down here. So then Paige cranked it up and took some data at 800 volts. All right, and boom, oh, wait a second, okay, so here was the original stuff at 700. We were running out of intensity, and she turned it up and got more peaks to show up. It looks like we're getting here. So there are a little bit higher intensity because we turned up the voltage on the PMT. Remember, the gain on the PMT is related to the voltage on it. And that if we turned it up even further, right, to 1,000, then boom, you can really blow up this region, right? And we get lots of extra peaks to help us get a much better analysis for the Rydberg constant. Now we can blow up this region, just hold down the cursor, draw a circle or a rectangle around there, and then we can expand that. You can see here originally, right, is the intensity pattern, this dropping off. Oh, okay, so we can definitely line these peaks up. We know those are good. And if we continue the intensity pattern, we go, oh, wait a second. All right, so these are good peaks. Here's a good peak, right? Which at 1,000 volts, we clearly get that, whereas when we looked at this at only 700 volts, we were starting to lose that and we didn't know what was going on. Let me expand this again. Note also that as you change the voltage, generally your baseline is going to change too, all right? So here, originally 700, we're losing, we just didn't have any signal left out here. We turn it up to 800, we get some more, but then we crank it up to 1,000. These peaks get much larger. Okay, so now we know this is a good peak, this is a good peak. Here we go, here's a good peak. We have overlapping spectra. It went over there. Yes, now for sure. Okay, that looks good. What about these next ones out here? Well, these might be a little bit problematic as we expand just that region. Definite, definite, definite. Yes, he's got a good shape, goes along with that, falling off in the right intensity pattern. And then one of these two, one of those, we might have, well, one thing we can do is we can actually analyze where those peaks were and see whether they fit on the line, because we're going to get a really good line and we could determine which peak was the next one that really fit by, does it follow in the pattern? There is a clear pattern in the spectroscopy, and therefore, right, since there's a clear pattern in spectroscopy, we can use that pattern to help us decide which is the next peak. Now, when we keep going out further and further in that direction, eventually, wait a second, here's an intensity pattern that's clear, and then boom, these peaks are going up and it looks like there's a new pattern. These belong to some different spectroscopic series for sure. There might be some stuff here that's either noise or an impurity. We don't just have H atoms, but we have other things, or they might be other series. So we're using the intensity and the wavelength pattern to tell which is the next peak we want, right? At first, it's pretty clear, the red, the green, the we get some blue and a violet peak. That intensity pattern's really clear. And then we get out here and we go, okay, we can continue that at higher gain, and we know which ones we want. Okay, boom, boom, boom. And then these ones, that's going to require some interpretation. One thing we got to see, do they fit the trend, right? Okay, so now what else do we want to do? What we want to do is we want to figure out where the peaks are, right, in wave numbers. In inverse centimeters, we're going to measure those rather than in nanometers. So we need to convert the wave length into wave number. How can we do that? Well, we can do that by a little calculation, right? We've got a wave that has all the wave numbers in it. We want to, or all the wavelengths in it. We want to convert that to a wave number. So first I want to make a wave for wave numbers that has as many elements as the lambda, the wave length wave, right? Okay, how do I do that? Duplicate. If I forget what that's like, oh, wait a second, I can go up here, duplicate waves. I can pick one of these and say, all right, I'm going to duplicate not the intensity, although the intensity has the same number of points, but I'm going to duplicate the wavelength one, and I'm going to turn that into a wave number for the same thing. Now here I gotta say overwrite because I've already done this example once, right? But if I forget how to write there, it tells me how to do it, or I could even take it to the clipboard and then I could put it in here and, oh, it would do the command, right? It would write the command for me. And then what I can do is just take this, copy and paste it a number of times, and then write out the names of the waves that I need to copy one on the other. And that way I don't have to worry about getting waves of the right length and all this kind of stuff. Then I need to do the conversion from wave length in nanometers to wave number in inverse centimeters. And the way I get there, 1 times 10 to the 7th divide by the wavelength in nanometers, you get wave number in inverse centimeters. So I do that calculation, boom. And now what I want to do is I want to fit a Lorentzian, it tells us, to our peak. All right, so let's take a peak. Let's say 410. It's a nice peak. Intensity versus not the wavelength, but the wave number of 410. Boom. All right, let's blow this guy up. Make it nice and big. There we go. That's looking good. And what I want to do is I want to fit, right, curve fitting a Lorentzian. So let's pick a Lorentzian. And the data I have on here is I410. And we're doing that versus wave number 410. Make sure you have the right one in there. Right. Okay, and we can fit that. And there is the central portion of the wave number. It'll also write it down here. Oh, it writes in one fewer. If I wanted to see it again, actually, it puts it into a wave, that's called W coef. So there's the exact value there. Or if I wanted to see it, I can always make a table and find that wave, W coef. And the W sigma is the, in this case, I did it as just a standard deviation. You don't need it in this case, but there you go. There is the central value and its standard deviation. So it's way out there. Now I've fit this entire wave to that, okay? That's fine if you only have one peak in here. That'll work pretty well. But what if there are multiple peaks in here? Okay, so what if, let's get rid of that. I don't need to save that. But let's say I did a region that had multiple peaks in it. Say right out here, 380. That's going to have multiple peaks in it, right? I380 versus wave number 380. Oops, there we go. Wave number versus, there we go. Boom, do it. Now we've got multiple peaks, right? I can't fit this whole thing to one Lorentzian. No, I need to fit one of these peaks. How do I do that? Oh, the way I do that is the following. I want to show info, and that way I get the cursors. If I get the cursors, then I can put the cursor on either side of the peak, right? And then, right, I go up here to analysis, curve fitting, choose the Lorentzian, and now it's 380 B, actually, in this example, versus 380. And I want to fit this between the cursors. All right, between the cursors, boom, I do it. There's the fit. There's the central portion. It writes that number up here so that I can read it down. I say, okay, and good. There's the fit, right? Doesn't look too bad. Does a Gaussian fit better? Let's take a look. If I want to see if a Gaussian fit better, I can just go back here and change it to Gaussian. Same data, also between the cursors. Boom, there you go. And there's the Gaussian. Hey, you know, they both fit pretty well. Maybe the Gaussian fits a little bit better, actually, right? There's the central value of the Gaussian fit. Boom, okay? We were told to use a Lorentzian, so what the heck, we'll use Lorentzian, you know, and what you'll see is that they both fit fairly well. The Gaussian and the Lorentzian really look different in the wings, all right? And they're giving you pretty much the exact same answer here, 26059, 26059. You know, the difference is out there in the tens place, that last significant digit that we want. You do want six figures, you want that tens place, and they're good out to there. If I want to, oh, I got to see that whole thing again, I do Command A, or in other words, I'm auto scaling this to see all the peaks again. All right. Oh, wait a second. This looks terrible. This is one thing that drives me crazy. Igor likes to, it thinks mostly engineers use it, so it uses engineering rather than scientific. And what I'd like to see is actual numbers and no exponent in this case. So I can just change that easily there. And again, if I was going to put a proper label on there, that would be the wave number, right, in inverse centimeters on that side, and its signal in volts on the other. And if I was going to be really nice about this, I would give that little box around here too, and things would look so much better, and we get a really looking like a real graph kind of thing. And if I wanted to show that fit on just this one, I could easily just blow up that portion of the spectrum to see how good the fit was. And you can see we're defining the center very well. The line shape might be a little bit funky compared to a true Lorentzian, but we're certainly finding where the center is very accurately of these. Okay, so I think that should show us what we there. If I wanted to save this, remember, just click on the red there. I could save this. It usually just calls it graph zero or something. Give it a name, you know, lore fit, and then you've got the name you want in there, and it will save those then to a macro. And if you want to see it again, you just call it out of there. Boom, there it is. Okay, so that is what we need. And then after you find all of these central peak values in where the peak position is in wave number in inverse centimeters, then you're going to do a plot. Plot that up and determine the, from a linear fit, determine the two ways to find the Rydberg constant. And that's what you're after.